So as you may recall, electrons are what we've been discussing the structure of for a hot minute now, because electrons are what take up most of the space within an atom. Electrons are what help you determine the size of the atom. Electrons are the answer. There are core electrons, there are valence electrons, there are lots of electrons. The size of the electron cloud helps you determine the atomic radius. So when we talk about atomic radius, we're talking about neutral atoms, and we're also going to talk about ionic radius, but hold that for a second, put a pin in it. Atomic radius, neutral atoms. Ionic radius, cations and anions and their radii. Which would we expect to have a greater atomic radius? Copper, gold, silver. I said that backwards. Copper, silver, gold. Said that backwards as the way it's listed. Sorry. Well, how do you know? We've been talking for a while about this formula. Q1, Q2 over D. And we have not substituted any numbers in there. We still won't substitute any numbers in there. But when the numerator is big, that requires more energy to pull away electrons. So when the core charge is big, that's what the numerator is representative of. When the core charge is big, it requires more energy to strip away those electrons. When the denominator is big, it requires less energy to strip away those electrons. So we've been talking about this formula in the context of ionization energies, but those same variables of charge and distance are going to help me determine atomic radius and ionic radius. So if I look at copper, silver, and gold in the periodic table, they're all three in the same group, the same column on the periodic table. And as I move down that group, what's happening to my shell number? What's happening to the distance between my nucleus and my valence electrons? The distance is getting much, much bigger. And when the distance gets bigger, obviously the radius gets bigger. So the furthest down on the periodic table is my biggest electron cloud. Gold is the biggest, silver is next, copper is the smallest. Yeah? I think that's kind of intuitive based on what we've talked about so far. Ionic radius gets a little bit trickier. Yeah, I said that. But let's keep talking about atomic radius for a moment. This is the actual trend. That's illegible back there. This is the actual trend. Atomic radius gets bigger as you move down a column. I don't want you to just know the trend. I need you to know why the trend is the way the trend is and be able to explain why the trend is the way the trend is. All right, what about aluminum, silicon, and phosphorus? Aluminum, silicon, and phosphorus, those are not upstairs, downstairs neighbors. Those are next door neighbors, all in the same period, but different columns in the same period, different groups in the same period. So what changes as you go across the periodic table? If I reference my formula that I just had to erase, is it the denominator or the numerator that changes across a periodic table? It's the numerator that changes across the periodic table. This guy has 13 protons. This guy has 14 protons. This guy has 15 protons. There's a bigger nuclear charge pulling on that electron cloud in phosphorus than there is in silicon or aluminum. So that shrinks your electron cloud a bit. When you have a bigger charge pulling, it makes your radius smaller. So aluminum is going to be bigger than silicon, which is going to be bigger than phosphorus. The copper, gold, silver trend, that's because the distance changes because you're going into new shells. The phosphorus, silicon, aluminum, that's because the core charge changes as you're going left to right across the periodic table. So the trend in atomic radius, we will see it later. I'm drawing a bad shape of periodic table right here, but I'm trying. Atomic radius gets bigger as you go left and bigger as you go down. Because core charge increases, it makes your electron cloud smaller. Okay, I think I've said that quite a lot of times. Moving on. Effective nuclear charge is what our textbook will call it. Core charge is what we will call it most often. So if we look at a sodium atom, a neutral sodium atom, it has a plus 11 nucleus, 10 core electrons, and 1 valence electron. Okay. This valence electron feels a core charge of plus 1 because the 10 core electrons are shielding. That's the term that we will see, shielding the nucleus. I got to click a few more times before you see this word shielding. If you look at magnesium, magnesium has 1 more electron than sodium. It's got a plus 12 nucleus, but still 10 core electrons, 2 valence electrons, and those 2 valence electrons feel a net plus 2 charge. So can you tell that my circle sizes are different here and here? Hopefully, yes. Higher core charge, higher Z effective, higher effective nuclear charge, higher number in the center of this nucleus is going to pull my radius in to be smaller. Plus 1 core charge, bigger radius, plus 2 core charge, smaller radius. Yeah. This shielding constant is what I was referring to a minute ago. The shielding constant is related to the number of core electrons. If you look up actual effective nuclear charge numbers, they're almost never whole numbers, but we're always going to talk about core charge, and core charge is a whole number. The concept is the same, and it gives you the same answers relatively. We won't ever calculate our Z effective officially decimal form. Okay. So we've said atomic radius trends go this way. The reason they increase across that way is because you have a smaller core charge going right to left. The reason it increases going down, you're adding new shells to your electron cloud. Okay. I think I'm getting it. Well, let's throw a kicker in there. Ionization energies are what we are using to help us determine what this electron cloud looks like. And if we look at a table of or a chart of ionization energies, we can see that there are a lot of high points on these ionization energies, meaning it takes a ton of energy to remove an electron from helium, a ton of energy to remove an electron from neon, a ton of energy to remove an electron from argon, krypton, xenon, radon. Ooh, there's something that seems to be especially stable about the noble gas configuration, noble gas electron configuration. So these guys are what everybody wants to be like. What? Yeah. Everybody wants to be like neon or argon or krypton or xenon or helium or radon. Yeah, everybody wants to be like the noble gases. So long ago, back in September, when we started learning about atoms, we said a sodium forms a stable positive, while an oxygen forms a stable 2-. The reason behind all of that information, why a sodium likes to be a +1 and why an oxygen likes to be a -2, 2-, is because of this stable noble gas configuration thing. When you look at sodium's electron configuration, it's neon 3s1. If you take away that 1 electron, you get a noble gas core. Fluorine is 1 electron away. If you add an electron to fluorine, it becomes a stable noble gas thing like neon. That's why F- is the way F wants to be. Oxygen is 2 electrons away from becoming like neon, so add 2 electrons to oxygen, you get a neon configuration. Take away 3 electrons from aluminum, you get a neon configuration. So these noble gas states, these noble gas configurations, are the thing that everything is aiming at, the configuration that most elements are aiming at. So that's why things that are on this side of the periodic table, things that are over here would much rather lose electrons to become like this. Things that are over here would much rather gain electrons to become like this. But everybody wants to be like this. These transition metals, they also lose. Okay, a new term. All of these elements, sodium, all these ions, sodium plus, aluminum 3+, fluoride minus, oxygen 2-, are all isoelectronic with neon. That means they all have the same number of electrons as neon. What neutral atom is isoelectronic with calcium 2+? All you need is the periodic table to answer this. Here's calcium 2+, tiny, tiny, I know. If I take away one electron from calcium, it makes it have the electron configuration of its neighbor, potassium. If I take away another electron from calcium, it makes it behave like the noble gas on the row prior to calcium. That's argon. Take away 2 electrons from calcium, neutral calcium, you get argon. So that's why calcium makes a stable 2+. These are the charges that we have seen before. Lithium likes to make a 1+, so does everybody in his same column. Magnesium likes to make a 2+, so does everybody in his column. Fluoride likes to make a 1-, so does everybody in his column. That's because they're all trying to achieve a noble gas type configuration. This is easier to understand in these corners and this corner. This transition metal stuff gets a little more hazy than that. Okay, so we're talking all about radius in this video, and we said we will have atomic radius and ionic radius that we will discuss. A trend in atomic radius is very clear. Ionic radius always forces you to think about how the electrons are arranged and how the core charge and valence shell relate to each other. However, anytime you have a cation, the cation is always smaller than its neutral atom. Because the core charge, the number of protons in the middle, let me say it that way, the number of protons in the middle has not changed. The only thing that has changed from here to here is you've lost an electron. And when you have fewer electrons being pulled on by the same number of protons, that radius gets smaller. When you add electrons to things, you have the same number of protons in chlorine and chloride, doesn't matter. When you add an extra electron, it grows your atomic radius, your ionic radius, to be bigger. Anytime you have a cation, it is always smaller than the neutral version. Anytime you have an anion, it is always larger than the neutral version. So knowing how ionic radius changes is going to be an important comparison for us to make, and we will even make comparisons with things like S2- and K+, and we have to decide if who's bigger. So now that we've talked about electron configuration and how it affects atomic radius, we need to talk about how electron configuration changes when you add and subtract electrons. Where do those electrons come from? If you're removing electrons, where do they come from? Transition metals, that's the D block of elements, remember. Transition metals, when you form cations out of transition metals, you always remove from the S subshell before the D subshell. So what I'm saying is, if I have titanium, which is argon 4s2 3d2, and I make a titanium 2+, you remove from the S first. So titanium 2+ would be argon 3d2. Argon 3d2. This is almost always left out, but sometimes you might see it there as an indicator that it used to have electrons and it's now empty. This is what we really see it as most of the time. If I make a titanium 3+, only after my S is empty do I pull from the D. So titanium 3+ becomes argon 3d1. Yep, argon 3d1. Manganese, you always pull out of the S first. So manganese 2+ is argon 3d5. You must pull out of the 4s first. Why do you pull out of the 4s first? Because it results in lower energy. Really, the reason for doing so much of the things that we do is to obtain lower energy. It's all about the energies. I'm tired of talking, but I got some more to say. Apologize. Ionization energies. We've been talking about them for at least 2 weeks now. Ionization energies. The minimum energy required to remove an electron from a gaseous atom in its ground state. What? It's the energy required to rip an electron away from an atom. So put in energy, it's an endothermic process, put in energy and rip away an electron. Ionization energy trends and atomic radius trends are very neat on the periodic table. They're opposite. So if this is my periodic table, ionization energy increases as you go up. Why? Because electrons are getting closer to the nucleus. Atomic radius increases as you go down because the electrons are getting further from the nucleus. Distance is the same variable, is the variable that's changing here, and it's equal and opposite in how it affects ionization energy and atomic radius. Further it is from the nucleus, the easier it is to ionize. All right. Atomic radius, we said, increases as you go left. Must mean ionization energy increases as you go right. That's because of the core charge. The effective nuclear charge is changing as you go across a period in the periodic table. So ionization energy is ripping away electrons. And IE1 means going from a neutral atom to a 1+. It's called the first ionization energy, taking away one electron. Going from the cation to a 2+, that's the second ionization energy. Going from the 2+ cation to the 3+ cation, that's the third ionization energy. Going from the 3+ to the 4+, fourth ionization energy, the trend continues. The third ionization energy is always greater than the second, which is always greater than the first. It's always easiest to remove the first electron. It gets successively harder as you remove more and more and more electrons. So here's a little table of electron ionization trends. And what I can see is sodium 496, so 500-ish, to just under 5,000. Removing one electron takes 500 kilojoules per mole. Removing the second electron, almost 5,000. Removing one electron from magnesium, 700, then 1,400, then 7,700. 500, 2,000, 3,000, 11,600. What this is telling me is there's something different about these electrons in the blue box. There's always a significant jump, a significant increase between the ionization energy in the white area versus the ionization energy in the blue area. That's because the blue area are the inner shell core electrons. So when something has 1, 2, 3, 4, 5 numbers that are relatively small, and then the sixth number is giant, that tells me that it has 5 valence electrons, because those 5 electrons were comparatively much easier to remove than this sixth electron was. A large change in successive ionization energies occurs once the valence electrons have been removed. So sometimes we may see a plot like this, where this is ionization energies and ionization numbers. So there are 4 electrons that are relatively easy to remove, under 10,000 kilojoules per mole, and all of a sudden, boom, the 5th electron takes 40,000 kilojoules per mole to remove. I would say this thing has 4 valence electrons. Knowing that it's a transition metal that has 4 valence electrons must mean it is titanium or zirconium or hafnium, something that has 4 valence electrons and is a transition metal. I am almost done talking. I'm real close, but I'm just not quite there yet. Noble gas configuration is very stable. That's the hills on this plot that we have seen previously. But there's something extra special happening in addition to this noble gas thing where, where, there's a little funny bump along these parts. There's a little hill and then you dip back down. Why? This little hill belongs to nitrogen. That little valley belongs to oxygen. This little hill belongs to beryllium. That little valley belongs to boron. Let's talk about beryllium and boron and nitrogen and oxygen and why they have this odd trend instead of just a forever increasing kind of thing. beryllium and boron, nitrogen and oxygen. We'll start with beryllium. Beryllium has 4 electrons, so it's 1s2, 2s2. It's got a core charge of 2+. That's, remember, number of protons minus number of core electrons is core charge of +2. Boron, there's his electron configuration, 1s2, 2s2, 2p1. Boron is 5 protons minus 2 core electrons to give us a +3 core charge, or Z effective, approximately +3. Our little diagram that I started to draw earlier that we don't quite understand why it looks the way it looks until we get through quantum numbers. Our little diagram looks like this for beryllium. Our little diagram looks like that for boron. Every arrow is representative of an electron. So beryllium has 4, boron has 5. Remember, every little line can only hold 2. So beryllium has a 2s that is completely filled. So does boron. But then boron continues to put more electrons in a higher energy subshell. Well, filled subshells are stable. Filled shells are stable. That's where the noble gas stability comes from. But filled subshells are also stable. So that's why it's more difficult to rip an electron from beryllium than it is to rip an electron from boron. Boron's got this one lonely electron. It's kind of easy to remove that one lonely electron. Much tougher to remove this one that's already in a filled subshell. So that's beryllium and boron. What about nitrogen and oxygen? There's nitrogen. He's got 7 electrons total minus 2 core, Z effective +5, core charge of +5. Oxygen is 8 electrons total minus 2 core electrons gives me 6 valence electrons. Sorry, and a +6 core charge is really why I was doing that math. Here's my little arrow diagram. Here's my little arrow diagram. What's the difference here is I've got 3 electrons, 1 in each orbital in nitrogen, and I've got 4 electrons, 1 in 2 of the orbitals and 2 in 1 of the orbitals. I feel like I'm saying this in such a weird way. But this one is completely half full. This one is more than half full. Half-filled subshells are relatively stable. So it takes more energy to remove an electron from nitrogen because you're coming from this reasonably stable half-filled subshell than it takes more energy to remove an electron from nitrogen than it takes to remove an electron from oxygen, because oxygen has this oddity that it's more than half-filled. The pairing energy is what causes this trend to be the way it is, but we're not going to go any further than that into what that means. We'll talk about quantum numbers next. It'll be great. Goodbye.